Carbon-13 NMR is used together with the proton NMR data in order to determine the structure of the molecule. We cannot rely on just the carbon-13 NMR to get the full structure of the molecule. It takes more time to run a carbon-13 sample than a proton NMR sample. So with carbon-13, it determines the number of carbons now in the molecule. So every different carbon will show a signal. We're going to use the same concept of shielding and deshielding that we used with the proton NMR. So carbonyls, these are electronegative compounds because of the sp2 hybridization of the carbon and the electronegativity of the oxygen. So normally carbons that are present next to the carbonyls, those are going to be shifted downfield because they're going to be deshielded. The signal for the carbonyl itself shows at 200 parts per million. And this is something important because carbonyls, they don't show in the proton NMR unless they are coupled with a hydrogen. Like, for example, aldehydes, carboxylic acids. In the proton NMR, we had the aldehyde in there showing at 10 parts per million. It's the proton that shows at 10 parts per million, but the carbonyl does not, of course, show. Same thing for the acid with the proton NMR. It's the hydrogen here that shows at 12 parts per million. So I have no idea about the carbonyls in the proton NMR. So this is why if you have a carbonyl in your structure, it is useful to look at the carbon-13 spectrum and see if you see anything around 200. If you see around 200 a peak, this means that it is a carbonyl. Now, carbon-13 NMR spectrum is much simpler than the proton NMR spectrum, and the reason why, because we can suppress the splitting pattern. There is no splitting between the neighboring carbons because the possibility of having two carbon-13 isotopes next to each other is almost zero. So this is why there is no carbon-carbon splitting in carbon-13. This is why you see that the carbon-13 spectrum is much simpler than the proton NMR spectrum. No splitting means that you don't do any integration. So there is no integration whatsoever in carbon-13 NMR. So all the peaks in the carbon-13, they are going to appear as one peak. So every different carbon has a signal, and if you have a symmetry, then in this case, you're going to end up having one type of carbon and one type of signal in the carbon-13. Here I do have two types of signals. The carbon over here is connected to the chlorine. Chlorine is an electronegative element. It causes deshielding. So I'm expecting carbon B to show further downfield compared to carbon A. Now here I have three different types of signals. The difference here is that I will see the signal for the carbonyl of the ester in the carbon-13 NMR, and I would apply the same rule of deshielding. Oxygen causes more deshielding than the carbonyl, so I would see the signal of the carbon C to be further downfield than the signal of carbon A. Carbon A is going to be a little bit upfield. Carbon C is going to be downfield because oxygen causes more deshielding than the carbonyl. But the signal of the carbonyl itself is going to be the farthest downfield because this one occurs at 200 parts per million. You can use the carbon-13 table that you have on eCampus with all the chemical shifts. You don't have to memorize any of those shifts in there. So the closer is the carbon to the electronegative element, the further downfield its signal will be shifted. So you can see here that carbon C will be further downfield compared to carbon A, which is far away from the oxygen. The signal of the carbonyl is going to differ, and it's going to range between 160 to 110 parts per million, depending on what carbonyl you are working with and what is connected to the carbonyl. So if the carbonyl also is connected to an electronegative element, it's going to shift further downfield. If it's connected to the benzene, also it's going to shift further downfield. It has all the way up to 210 for the shift. So with carbon 13, it's not necessarily the carbon to have a hydrogen to have a signal. Carbons that don't have a hydrogen, they have signals as well. So here, if I want to count the number of signals, that's going to be signal A, that is going to be B, this is going to be C, that is going to be D over here. All of them are different. So it's going to be E, this is going to be F, and that is going to be G. So I'm going to end up getting 7 carbon signals. Every different carbon will have a signal. For the benzene, the signals of the carbons of the benzene, not the hydrogens, the carbons of the benzene, normally they do occur in this region. Now we know that we can simply identify the hydrogens on the benzene in the proton NMR, but this is an additional information that if you see a lot of peaks between 120 and 150, this is purely for the carbons of the benzene. So each of these carbons in there will show between 120 and 150. So you go over here in the carbon 13, and you can easily see between 120 and 150, you have a lot of peaks in there. Each peak corresponds to the different carbon. Count them, and these will be the carbons of your benzene. Now, for the scale of the carbon 13 over here, the scale is a little bit bigger than that of the NMR. So the NMR is between 0 and 12 parts per million. The carbon 13 is between 0 and 200 or 210 parts per million. Splitting gives you information about the environment around the carbon. So there is no way that you're going to have a carbon 13 next to each other. But there is a possibility that you have a carbon 13 and a hydrogen 1 that are on the same carbon. So you can have hydrogens here that are on the same carbon. And as the carbon spins, as the nucleus of the carbon spins, the nucleus of the hydrogen is going to spin as well. So this hydrogen, when it spins, it's going to have an effect on the splitting of the carbon. Unless you suppress this hydrogen here and you don't allow it to spin. So if this hydrogen is suppressed and it's not allowed to spin, then in this case, you will see all singlets with the carbon 13 spectrum. So it's going to be run under broadband decoupling, similar to this. There will be no splitting whatsoever, and every peak represents just one carbon, a different carbon in there, and you have no information about the hydrogens that are on the carbon itself. On the other hand, if you wish to know how many hydrogens each carbon is connected to, then you run the spectrum over an off resonance decoupling. What is that? This means that as the carbon is spinning, the hydrogen is going to spin. And when the hydrogen spins, it's going to go and split that carbon into multiple peaks. The rule that we're going to follow is the same rule as we did before for the proton NMR, which is the N+1 rule, but one deviation here, that we are looking at the hydrogens that are connected directly to the carbon, not to the adjacent hydrogens. So this carbon over here is going to be split into 3+1, so it's going to be a quartet. This hydrogen over here is going to be split into 2+1 because it is connected to 2 hydrogens here. Again, as the carbon spins, as the hydrogen is going to spin. And if there's nothing to suppress the spinning of the hydrogen, then the hydrogen is going to split the carbon into N+1 peak. So this is going to be a triplet. This carbon over here is going to appear as 2+1, so it's going to be a triplet as well. In most of the cases, you're going to see the broadband decoupling spectrum, so there is no splitting. If you are going to see the off-resonance decoupling, then I will supply you with both spectrums, and they will be on top of each other. So you're going to see the broadband decoupling, And then on top of the broadband decoupling, you're going to see an off resonance decoupling in there showing the splitting for each of the signals. Same thing over here for this example. So this is going to be a quartet. This is going to be a triplet, 2 plus 1. This carbon here is going to be a 0 plus 1 because it has no hydrogen. So it's going to be a singlet, and that is going to be a quartet. Knowing the splitting pattern will give you information of the hydrogens that are directly connected to the carbon in question. With carbon-13, there are more options that we can include when we are running the spectrum to count the hydrogens that are attached to the carbon. One of them is adding a second transmitter, and that process we call it distortionless enhancement proton transfer, DEPT. And we can put that transmitter at different angles, 135, 90, or 45. Those angles will eliminate different type of hydrogen. For example, the DEPT 135 will show positive peaks with CH3s and CHs. So let's say if I have a CH2 in my structure, then the CH2 is going to appear as a negative peak. Then I would know that I have a CH2 in here. Normally, the DEPT spectrum will be above the original carbon-13 broadband decoupling spectrum. So you will have the broadband decoupling spectrum, no splitting, and then above that, you're going to see your DEPT in there. DEPT 135 is the most useful because it tells me whenever I have a CH2, it's going to show all these negative peaks for the CH2. You count them and you know how many CH2s you have in your structure. It's going to show a positive peak for carbons with hydrogens. So if you have a CH3, it's going to show. If you have a CH, it's going to show. It's not going to show carbons with no hydrogens though. So the carbons that have no hydrogens are going to be nulled, and the carbons that are CH2s are going to be inverted in the DEPT 135. In the DEPT 90, if you run that, it's going to show only the CHs as positive peaks. And then after that, you're not going to see any of the peaks unless you have an aromatic CH. Then the aromatic CH will show in the DEPT 90. Then you know that you have a benzene in this case. DEPT 90 is good for indicating benzene. But remember that you can indicate or you can show benzene also with proton NMR in the region between 7 and 8 parts per million. So this is an additional information. Other than that, DEPT 90 will show nothing except if you have a CH. So it will show the CH in there, whether the CH is a benzene or it's a regular CH, then it will show it as a positive peak. If you have benzene that has no CHs in there, meaning that all the carbons of the benzene are occupied. So if you have a benzene and all its carbons are occupied in there, so there is no CH, you're not going to see any signal in the DEPT 90. The DEPT 145, though, shows no signal for the carbons with no hydrogens. So no signal for carbons with no hydrogens. So if you look at the carbon-13 spectrum, you would see the carbonyl that has no hydrogen, but you won't see it in any of the DEPTs, which is a very useful information here that you would know that you have a carbonyl in this region. Also, carbons with no hydrogens, they do appear in the original carbon-13 broadband decoupling, but they will not appear in any of the DEPTs. Okay. This table over here, you can have it in the exam. It's found in the list of tables on eCampus. If I am comparing between the broadband decoupling carbon-13 of this molecule and its DEPT 135, you can easily see that you have 3 CH2s in there. So you're going to see them inverted. So you know that you have CH2s there. And carbons that have no hydrogens will not appear in the 135, but they will show in the broadband decoupling. So this means that this carbon and this carbon will not show in the DEPT 135.